Hey everybody, welcome to lesson 7 for social justice math. Today concerning expected values. We are going to have a short one today, primarily focused on the one thing that everybody loves, and that is money. So there are a lot of places where expected values show up in everyday life. And we'll talk about what expected value is, and we'll give an example of that using the lottery. So not just money, but free money. So before we get to free money, of course, while I have you here, I have to talk a little bit about math. So we have a couple definitions that I want to go over before we actually start doing this. We have a probability distribution, right? And this is just a table that gives us a probability value for each potential value of, we're going to call it X right now, but really X is just whatever outcomes we are looking at for a specific situation, right? So mathematically, we'll use X as what we call a random variable. So it'll be a stand-in for whatever our outcome is, right? But an example of that, to make this a little more concrete, let's say that in elementary school, half of the students come from low-income homes and take part in our free lunch program. So with that, right, we have students sitting at desks of 4, and we could say, right, if we go up to a random table of students, right, how many of them would we expect to be on free lunch? Right, how many would we expect to take part in this program? So we have a couple different values for X that could happen, right? Could be that all 4 of the students, right, at this table or this group of desks are on the assisted lunch program, right? So that would be a possible 4 as our outcome. Could be the 3 of them, or 2 of them, or just 1 of them are on the program, or it could even be that none of them are on the program, right? That all of those 4 students bring their own lunches, right? So now we have to figure out, since we have our outcomes, what are the chances of each of those occurring, right? So let's look at it this way. We have 4 students. Each one, right, has a 1/2 chance of being on the assisted lunch program, assuming they're assigned seats randomly, right? Half of our students participate in this lunch program. So you would say, right, kind of intuitively, well, we would expect 2 students at each table to be on it, right? So now let's see if the math backs that up. Let's start at the outside edges. That's the easiest one, right? If 0 students are on it, none of the students are on the assisted lunch program. Each one has a 1/2 chance of being on it, which means a 1/2 chance of not being on it. So I would do 1/2 for the first student times 1/2 for the second student, the probability that they aren't on it, times 1/2 for the third student, times 1/2 for the fourth student. So that looks like 1 over 2 to the 4th power. 1 over 2 times 2 times 2 times 2, right? So 4 times. So 2 times 2 is 4, times another 2 is 8, times another 2 is 16. So I get 1 over 16. So the probability that all 4 of the students are not on our free lunch program is 1 over 16. So that's where we get this number over here. Now on the other end, right, we also have 1 over 16, and that's because the probability of being on the lunch program is the same as the probability of not being on the lunch program, because it's a 1/2 chance either way. So it's just a coin flip. So the probability of all 4 students being on it, right, is going to be 1/2 times 1/2 times 1/2 times 1/2. Right. Now we can say for 1 student being on it, right, we could make a similar argument, right, and say like, well, the first student has a 1/2 chance of being on it, and then the second student has a 1/2 chance of not being on it. But we have to be a little careful here because it doesn't say which student is on the free lunch program. So really what we're looking at here is, out of the 16 possible scenarios, right, how many of them have exactly 1 student on our free lunch program? Well, either the first student could be on the free lunch and the other 3 not, Or the second student could be on free lunch and the other three not. Or the third student and the other three not. Or the fourth student, oh, there we go, got my fingers to work. There we go. 3 students not on it, 4 student on it, right? So there's 4 possible scenarios here, right? So 4 scenarios for 1 student being on the free lunch out of 16 total, so it's 4 over 16. It kind of works like our proportions, like we had before, right? Number of outcomes we're interested in, right? Total number of outcomes. So you can repeat this for 2 and 3. For 3, it's really easy. It's just instead of 1 person being on assisted lunch and 3 not, you would have 3 on assisted lunch and 1 not, and that 1 could either be the first, the second, the third, or the fourth student. For 2, right, we could have the first 2, we could have, there we go, we could have the first and the third, we'd have the first and the fourth, we could have, can I do it? There we go, the second and the fourth, or the second and the third, or the last 2. So that's 6 total, as you watch me horrendously display my lack of dexterity. 6 total out of those 16 options, right, for 2 students. This is kind of the gist of how we come up with these things. But at the end of the day, we have a chart. One side here has our outcomes, that's our X, and then our P of X, our probability of X, is the probability of each of these numbers happening. So now that we have this, we can answer some actual questions about this thing, right? So what is the probability that X is at least 2? Well, at least 2 would be 2, 3, and 4. And all I have to do is add those together. So with fractions, right, same denominator, I just add the tops, right? So 6 over 16, 4 over 16, and 1 over 16 is 6 plus 4 plus 1, which is 11, all over 16. So 11 over 16, right? That would be the probability that X is at least 2. What is the probability that X is an odd number? Is what this says down here. It's kind of cut off. Well, our odd numbers are 1 and 3. 0, 2, and 4 are even numbers. So if I look at 1 and I look at 3, that's 4 plus 4, right? So 8 over 16, or we could reduce that down if we wanted to 1/2, right? 8 over 16 would go to 1/2. So here's a couple rules when it comes to probability distributions, and these are things that can be very helpful. The sum of all the probabilities in the distribution must equal 1. We've actually kind of used this fact before, especially when we did proportions and hypothesis tests, right, where we took a sample and we broke things down into like a yes or no or this or that kind of thing, right? And I said, well, if you have 1, you just do 1 minus the other, and that gets you the other one. So if we had P, we would do 1 minus P, and that would get us Q. This is really what we're using here, right? If we look at all the possible outcomes and we add them all together, right, then they have to equal 1. And the idea behind this is that, well, we go back to our example. If I say I have 4 students at a table, what's the probability that either 0, 1, 2, 3, or 4 of them are on assisted lunch? What I'm really just asking is, I have 4 students at a table. What's the probability I have 4 students at the table? It's just 1. It's 100%, right? So that's a nice thing that comes in handy. The other thing is, all of our values for probabilities have to live between 0 and 1. Now, they could be 0, they could be 1, right? They usually won't be, but they could be. But they have to live between 0 and 1. So if you ever get a probability of 1.5, or you get a probability of 3, or you get a probability of 500%, you done goobered somewhere, right? So this is a nice way to check your work, right? If I do out the calculations and I say it was probably the 2 students at this table on free lunch, that's 300%. I done messed up somewhere, right? So this is a good way to check your work. So a couple examples of other times probability happens, right? What is the probability distribution for flipping a coin? Well, we have 2 outcomes, heads or tails, right? We're not assuming that like it's going to land on its edge and stay there, or like we're going to flip it and the hawk's going to grab it mid-flight. We're ignoring those for now, right? So we just have heads or tails, right? So those would be our 2 outcomes, and then the probability for each of those would be 1/2 for heads, 1/2 for tails. What's the probability distribution for rolling a single-sided die? Well, single-sided die, we're going to say it's 6-sided. If you know that there are other types of die, then you might be a nerd, but it's okay because I'm also a nerd. So I'll go ahead and note myself here. There are a lot of different types of dies. So there you go. you're a nerd, don't feel alone. So we have 1, 2, 3, 4, 5, 6 as our possible outcomes, right? And what is the probability of each of those occurring? Well, they have an equal chance, all with 1, 6. So our table would look like 1, 2, 3, 4, 5, 6 down our column for X. And then for our probabilities, it would all be 1/6, right? Now, what's the probability distribution for a total rolled on a pair of dice? So I rolled 2 6-sided die and I add them together. Okay, now we're getting fun, right? So now we need to go back to what we did before and start thinking about the different possibilities. So for example, right, how many ways can I roll a sum of 2? Well, there's only one way, right? I have to get a 1 on both die. So that's one total outcome, right, where we get a 2 over how many total? Well, there's 6 possibilities for one die, 6 possibilities for the other. So I multiply those two and I get 36. So 1 out of 36 chance I get a 2. And similarly for a 12, I'd have to get a 6. And then I have to get another 6. So I have to have a 6 on both dies. So one possible outcome out of 36 total. Now for something like a 3, right, I have 2 possible outcomes here, right? One die could be a 2 and the other could be a 1. Or first die could be a 1, the other one could be a 2, right? So we have a couple different possibilities there. So that's 2 out of 36, right? 2 good outcomes over 36 total, or 1 out of 18 if we want to reduce. So I'm going to let you fill out the rest of that table yourself to make sure you have this down. So think about how many different ways we could get the number we want, right? How many ways would I get 6 on 2 die, right? I could do 2 and 4, 4 and 2, I could do 3 and 3, I could do 1 and 5, I could do 5 and 1. So make sure you have all the ways for each one and go ahead and fill in that chart to practice. Right now, when we have a probability distribution, one of the first questions we run across is, what would we expect to happen on average over time for a situation like this? Right, so in order to do this, what we would do, right, is take our X, so our outcome, times that probability, right, and make a third column that's just the X times the probability. And then what we're going to do is we're going to add up that column. So on a 6-sided die, right, we would take our outcome of 1 times the probability of 1/6. That would give us 1/6. We put that in the next column. 2 times 1/6 gives us 2/6. We put that over here. 3 times 1/6 gives us 3/6. Put that there. You see where I'm going with this, right? And then we add all those up at the end, and that will give us our expected value. So expected value for rolling a single die, right? I'm going to let you know now that is 3.5, right? Which is weird, right? I can't roll a 3.5 on a die. Right? So this actually highlights something really important about our expected value, right? This is what we expect to occur on average over time, meaning if I rolled a die 100 times and I took the average of all those rolls, I would expect it to look like 3.5. Right now, an average can absolutely be 3.5 when we're rolling that stuff. We can get decimals there. So this is not necessarily like I do the thing once and this is what I expect, right? We're talking about on average over time. Now, a pair of dice, if we roll that and we look at the sum of those, I'll leave you to figure that one out on your own using this method we talked about. So single die should get you 3.5, right, when we do this method. So double check yourself, make sure you're getting 3.5 there. And then let me know what you get for a pair of dice. Okay, so gambling aside, let's talk about gambling, right? From dice to Powerball lotteries, let's see where expected value comes into play with this, right? Let's suppose we spend $2 on a Powerball ticket and we look up the odds of winning the lottery. Now, this is from actually Valentine's Day of 2019. So we have a grand prize here of $159.1 million. And we have the odds of actually getting that prize. The odds are 1 out of 292, 201, 338. Now this says odds, they actually mean probability here. So if you know, if you've taken statistics before, if you know about this, odds and probability are slightly different. So they use the term odds here, but they actually mean probability. So this is basically the chart we made before. These are our X values. These are possible outcomes. And this, right, is the probability of each of those occurring. Okay, so we have our X's. We have our odds here. All I have to do is multiply across here, get a decimal, right? Fraction if you want, but decimals are easier to add. So I multiply this number times this number. I get this. Go down to the next row. 1 million times 1 over 11,688,53. Get this number. And I do that all the way down to the bottom. So the last one I do 4 times 1 over 38, and I get 0.1052 and some extra stuff. Okay. So this is our money, our prize money, times our probability. Now that I have that, I'm just going to add them all up. So straight down the column, and that is going to give me my expected value. So my expected value here is 0.865 to stuff and things. Now we're talking about money, right? This is the amount of money we're winning. So our expected value is about 87 cents. So on average, if we played this lottery over and over and over again with these exact same odds and these exact same prizes, we would, on average, expect to get 87 cents back on our $2 investment. Okay, so we spend $2 on the ticket, we expect to win 87 cents. So, of course, the big question, right, is should you play this lottery? And I think there are actually valid reasons for both of this. If you're playing it because you want to win money, please do not play this lottery. You're not going to win money, right? Now you could get extremely lucky and hit our jackpot here, right? And then you're set. But on average, what you would expect is to actually lose a little over 50% of the money you're putting into it. So not exactly the smartest investment. This $2 is better spent elsewhere, even if it's just going to Sonic and getting you a drink. Now, if playing something like the lottery makes you happy, right, there are far more expensive ways to make you happy. And so if you enjoy buying a lottery ticket and looking forward to seeing what the numbers are when they're picked and, kind of planning out what you would do with the money, and that's worth $2 to you, then go for it, right? Because, people spend $2 on entertainment all the time. A movie is far more than that. Somebody buys, a pack of baseball cards or magic cards, that's going to be more than this. And it's essentially the same thing, right? You're just trying to collect things. You could buy those little mini, I don't even know what they're called. I'm showing my age, but the little mini brand things, So if this makes you happy, go for it, right? This isn't about telling you what conclusion to come to. This is about making sure you have everything you need to come to the conclusion that is best for you. So with that being said, we have our test 2 next week. Now this is actually true regardless of what semester you're in, because if we're covering this, that means that our test is in fact next week. And if we're in the summer, then our test is next week anyway, because it's every other week. So we will have our test 2 coming up. This material will be on test 2, right? If you're in the actual semesters, the fall or the spring, then of course this worksheet will be due with the other ones at the beginning of the test. But if not, then it will be due at the end of the week, right? If you're in the summer. So with that being said, I want to thank you all for watching. Thank you for your time. And I will catch you in the next one.